Okay, we are now recording. All right, let's continue our discussion on memory. Today, it's going to be a short lecture. Main reason is I have to give an exam at 10:30, for which I need to be back home so that I can do the online proctoring and setup. So hopefully we get done in an hour 15 minutes tops today, similar to the class before. So it shouldn't be that bad. And then everybody is glad that, oh yeah, I woke up early and my day is going to be good now, right? Okay. Last few times, what did we talk about? Virtual memory, memory organization, memory hierarchy, pages, frames, page faults. These are the kind of things that we've been talking about. In the last one, it was a simple lecture on page replacement algorithms, right? On what basis do you replace the frames in physical memory? Do you do FIFO? Do you do least recently used? Or do you do optimal? Well, you can't. You can use that for a benchmark. Or do you do some approximate LRU scheme for page replacement? So that's where we are. Now, today we are going to be talking about frame allocation. You have many programs, and if it's an active program, it's a process, right? If a program is actively running, it's called a process. You have many processes. You have limited number of frames in your physical memory. How are you going to allocate? Program 1 gets 2 frames, program 3 gets 10 frames, so on, right? How are you going to allocate that? So frame allocation scheme, on what basis do we do this on? So some things that are simple and some things that are more realistic. Then we'll talk about a related concept of thrashing. Thrashing essentially means programs do not have enough frames in the physical memory to make progress, so they keep page faulting and they don't make any progress. So that's called thrashing, and we'll talk about that as well. So just to give you guys a quick recap here, instead of starting with a 1, let me start with a 0 here. So how do you handle page fault? Well, let's say we have an instruction, some load word instruction that the CPU generated for which we need to access the memory. Clearly, we do, right? Because load word is a memory access. We are loading a word from the memory. So where do we look for the memory? Well, we look for the page table. Page table is going to give us the translation between what and what? Between a virtual address to the physical address. Well, the page table is not giving you the complete physical address, it is giving you the frame number. So it will take a look at the page number field and it will give you the frame number field. The page offset copies over directly. So that makes up your physical address, and then you go look at it in the physical memory, in the DNAM. However, if the page table indicates with its valid bit that the corresponding frame number is not present, if that mapping between the page number and frame number is not present in the page table, which is indicated by a valid bit of 0, then hopefully we have the corresponding disk address. So what do? That's a page fault, right? Valid bit is 0. So disk address is provided. Well, because of the valid bit being 0, the operating system initiates a trap addressing error. In response, it will initiate disk IO. It will go read the hard disk and then bring in the corresponding frame into the physical memory. And if the physical memory is full, we have a problem, then we'll have to use one of those page replacement algorithms that we talked about. If you have an empty frame here, then we don't have an issue. We know which way to put it. But soon after we bring things into the physical memory, we will update our page table. Our frame number will go over here, and this guy will now become a 1. A valid bit becomes 1. And then we'll restart the instruction, right? So now we have that mapping. Next, in all of this, there is a bottleneck. The bottleneck is right here. The secondary hard disk is slow, a lot slower than physical memory, let alone the cache, right? The cache is the fastest. So when you are accessing the disk, you're spending a lot of cycles. On average, that number is close to 80 million cycles. 80 million cycles, a process is just waiting to get that translation for a physical address, a frame number. What do you think we should do there? Just wait, stall? Maybe what we can do is, instead of working on this instruction, we can start working on some other instruction for some other process, right? So that's where we are going with this. So what should I do with the CPU when we have a page fault? And when we have a page fault, we need to go do a disk access, which is about 80 million cycles. Takes several orders of magnitude longer than a cycle time, about 80 million cycles, right? So do we just stall, or do we start working on other programs? Clearly, stalling is no good because we are just wasting all that CPU time. So working on other programs is a good option. But for that to happen, we should have other programs to work on, right? So we should have enough processes to work on to give you an option, right? Okay, if you are doing a disk access, you move to program 2, process 2, or process 3, or process 4. So if you have enough options, if the CPU has enough options of processes to choose from whenever it page faults, then it's good. Now, as you're increasing the number of processes, you're also increasing the degree of multiprogramming, right? You are able to work on multiple programs in parallel at once. So that's increasing degree of multiprogramming. So that's a better idea. Now let's talk about multiprogramming, multiple running programs. An active program is referred to as a process. Process, active program. CPU is right now working on this particular program called a process. Where do you look for processes? You guys have laptops. If you wanted to find out all the processes that are currently running, can you do it? Sure. How do you do it? Say on a Windows machine. Task Manager, right? So if you go into Task Manager, it'll give you the list of processes that are currently occupied in your physical memory that are using your RAM, and it'll give you percentages and all of that. And you know, if you look at the list, there will be a lot, right? Even if you just start off your, like boot your laptop, there will be OS related processes that will be running in the background. So even if you don't have any user applications going on, there will be some processes that are running for supporting the OS. Let's see, multiple programs are going to be sharing CPU and memory. So this is for an active program. Each process has different properties. Locality, this is what? How correlated are memory accesses in space and in time. That's principle of locality, two forms, spatial locality and temporal locality. And each process will have a different spatial locality and temporal locality. Priority, some processes high priority, some others being low priority. If you look at the operating system processes, those will tend to be generally high priority processes. Size of the program. Some applications will tend to be really, really large, while others can be very small. Now, these are going to be different, right? So each process is going to be different. You're going to have a different locality, different priority, different size, which means on what basis are you going to assign? Are you going to assign a higher priority process more number of frames? Are you going to assign a bigger program more number of frames? Are you going to base this on priority? On what are you going to base that frame allocation on? That's the question that we are going to try to answer. So when one process issues a page fault, valid bit 0, need to go to the disk, you switch the CPU to another process. And by doing that, you are increasing CPU utilization, because earlier you were working on one program that had to stall, and you're not wasting any time, you're starting to work on the other one, right? So you're trying to make sure that the CPU is in work mode almost all the time, at least as much as possible, right? So that is going to improve our CPU utilization. How do you do that? Well, in this case, you are going to launch more processes, right? So if you have more options to work on while one process stalls, then you are going to have a better CPU utilization, right? So in this case, it's a win-win, right? Why is it a win-win? I have one process, page faulted. In order for me to use up those 80 million cycles, I'm going to launch more processes. If I launch more processes, I not only have multitasking, but I also have that CPU utilization going up. Do you guys see that? So both are going up in the initial stage, but you cannot do this indefinitely. What is the problem when you do it indefinitely? If you keep increasing number of processes, what is going to happen? Earlier you had 1, then you made it say 4, and now you are increasing it like 5, 10, 20, 30. What is going to happen now? Think about the number of frames. You have a limited number of frames, right? 100 frames in the physical memory. You have to allocate that to 4 processes, 5 processes, 10, 100, right? So as you are increasing the number of processes, you still have a limitation on the number of frames, which means that each process will get a fewer number. So if each process gets fewer number, what is going to happen then? They are not going to be able to make progress, right? Everybody is sort of, oh, I need the disk. Oh, I need the disk. I need the disk, right? So everybody starts page faulting. That is called thrashing. So you can increase that number of processes, but to a certain point. After that, you will start thrashing. I feel like I've delivered the entire lecture with that discussion there. All right, let's see. We can move this down. Frame allocation. You have got the total number of frames, which is limited because why? It is a physical memory. We're not talking about the virtual address space. We're talking about the physical address space. I've got a 8 GB RAM. I've got a 32 GB, well, not 32 maybe, 16 GB RAM, right? So I've got physical memory that is limited. So number of frames will be limited. This is a shared resource. Operating system is sharing this resource. All the processes are sharing this resource. So you are going to have to pick the number of frames allocated to each process from that shared resource. We need some creative ways to allocate frames to processes. Let's talk about some allocation policies. The first one, very simple, equal allocation. Everybody gets equal share, right? So 10 processes, 100 frames, each one gets 10 frames. Not a good idea. It is simple, however, it's not a good idea because we are not basing that on priority, on size. We are not even changing it, right? So it's a simple allocation policy, but doesn't work. Next one is proportional allocation, and this proportional is relevant to the size, right? So a larger process will get a larger allocation. So base this on a weight, the weight corresponding or weight computed based on the size of the process. The next one is priority, larger allocation for higher priority process. So if you base it on size, it is a bit realistic. If you base it on priority, it is a bit realistic. If you combine both of them, base it on both priority as well as size, then it's very realistic. Now, this particular allocation could be global or could be local. What does that mean? Local essentially means that I have got a section of frames over here that I'm going to reserve for certain processes. So I can assign those frames from this limited set of frames, or global, all of physical memory. I can allocate frames from anywhere in my physical memory. Let's talk about equal allocation. Everybody gets the same. If you assume that the total number of available frames are going to be cap F subtotal, of course, this is after you have allocated frames for the operating system, and we assume that the total number of processes are cap P, then the allocation for each process is cap F divided by cap P frames. And we may reserve some free frames in the buffer pool so that by chance, if some high priority process comes in, we have some buffer to we have some frames in the buffer pool to take care of that particular process. Equal allocation scheme is pretty simple. We are allocating physical frames in the physical memory to processes that the CPU is currently working on. In equal allocation, if you have 10 active programs, 100 frames available, each one gets 10 frames. Equal. Next, proportional allocation. So allocate frames proportional to the size of the process. So certain processes tend to be really high. So give me some examples where your certain applications that take a lot of memory, a lot of RAM space. Was it? Chrome, it's a killer, isn't it? I hate it because of that, but I love it for other reasons. You guys agree? Have you guys checked out how big Chrome can get? Check it out. If you are a Chrome user, go to your task manager and try to look at its Cinebench. Yeah, Cinebench takes a lot of RAM. Now, if you are a video editor, then you will have a lot of programs on this list, or a lot of applications on this list, right? Video editing software can take a lot of RAM. That reminds me of one of the controversies that has been going on with the iPad. iPad Pros used to come in with, I believe, 6 gig RAM in the second generation of the iPads. 6 gig RAM was the total physical memory, but Apple put a limit on the max RAM per application. So each application could, at the maximum, use only 3 GB. So even if you have 6 gigs in total, that is, any app could use only 3 gig. You cannot, so no matter how many programs you have running, so even if you had just one app running, you couldn't use more than 3. And so all the users went crazy, right? Like, why can't we have more RAM than that? Because they want to be able to do video editing and whatnot on their iPads. They want to get as close to a MacBook Pro as possible, right? With the next generation, with the current generation now, they increase the RAM, say on the highest model, the best model, the iPad Pros, the top end model, I think it's 16 gig, right? So the RAM, you can go as max to 16 gigs of RAM. And with 16 gigs of RAM, they limited max RAM per app to be 5 gig. So many people were unhappy about that. Because even if you have like just, nothing running on your iPad, you've got 16 gigs available to you. And so you would think that I'll be able to use the video editing software very smoothly, but it doesn't work. Only 5 gigs. The 5 gig is the limit. So they've put a limit on that. They bought the M1 chip from the MacBook into the iPad now. Yeah, they did, absolutely. So the new iPads have the M1 chip. So everybody is happy about that. However, they're not happy, among other things, about this, that they put a limit on the number of frames or the physical memory that can be associated with each process. They put a limit on that. Let's see. Let's come back to this. Proportional allocation. Allocate frames proportional to the size. Let us say that our processes belong to this particular set, P sub 0, P sub 1, so on up to P sub I. Each of these are indicating a particular process. The size of any process, P sub I, we are indicating as S sub I. So S sub I is the size of process P sub I. The total process size is simply going to be the summation of all the sizes. Right? So summation over all I, small s sub I is going to give you the total process size, which is S. The total number of frames, cap F sub total. Allocation for each process is going to be proportional to its size. So find out the weight using the size of each process divided by the total size multiplied by the total number of frames. So you're finding out the weight that goes along with the frames by using this particular ratio, SI divided by cap S. Size of each process divided by total size. Questions here about proportional allocation? So if you know, for this, you need to know the size of each process. That might, in realistic scenarios, it might be some changing, right? It's not constant. It will be dynamic. So if we were to use proportional allocation, then we would have to change that scaling appropriately. But this is based on time, based on size of the program. In this one, in the equal allocation, there was no basis. You just had to be there. You're there, you get the equal allocation. You just need to be active. Next, priority allocation. So higher priority gets higher allocation. That's what you're talking about. This is allocation based on priority. So instead of the size, to compute the weight of F total, right? We are trying to scale F total. We'll use the priority instead. Now, if P sub I generates a page fault, if any process generates a page fault, select the replacement of one of its frames, right? That's one strategy, right? So if you are, hold on, what's that? For replacement, right? So when a particular process generates a page fault, select the replacement of one of its own frames. If you want to bring something into the physical memory, you can select the replacement of one of its own frame, or you can replace a frame from a process with a higher priority, right? Which is usually indicated by a lower priority number. So when you're trying to replace, you're trying to bring in frames that have higher priority into the physical memory compared to a lower priority when you have a page fault. Now, question is, how many frames do you allocate for each active process? You can be all the way over here, the minimum number, or you can be all the way over here, the maximum number of frames. So let's start over here, the minimum, right? So each process, this is for each process. A process is getting very, very few number of frames allocated to it. Well, if it's not even meeting the minimum, maybe the minimum is I need at least this many to start working on that process, right? Something that is enough frames to process an instruction function from the ISA. To do the basic, to get started. Even if we don't have that minimum, then we'll have to, if you are here, right, fewer than the minimum, then you don't have no choice but to suspend that process. Don't have any choice. So if you are at the minimum, you will be able to make progress. So we have just enough for that process to move ahead. So that's over here, all the way over here. You can keep increasing it, right? Now, as you are increasing it, what are you doing? For each process, you're saying, I'm allocating 2 frames, 10 frames, 50 frames. You're increasing the number of frames for that particular process. As you're decreasing that, as you're increasing that, what is happening to the page fault rate for that process? As you're increasing the total number of frames in general, so don't worry about Beladi's anomaly. As you're increasing the number of frames for each process, what is happening to the page fault rate? Goes up, goes down? Sorry? It should go down, yes. So page fault rate will go down, right? Page fault rate goes down. As you are increasing the number of frames that are allocated for each process, for a process. So that's good. But so you could stop here, or you could stop here, or you could stop here, or you could go all the way over here. So if you go all the way up to the max, almost like the entire physical memory is being associated with this particular active process. When that happens, of course, you are not going to get any page fault. Page fault rate has gone so low that you will not have any page fault. The problem with that is nobody else can have a slice of the physical memory, right? So because this is a function of how much physical memory you have. So if you allocate all of the frames to only one process, then you will be able to make progress to that process. However, nobody else will get any frames. So what does that mean? That means that the degree of multiprogramming over here is going to be just 1, right? Degree of multiprogramming goes down. So as you are moving this way, your page fault rate is going down, which is good news, but your degree of multiprogramming is also going down, right? As you are going up, if you are here, you will not be able to assign frames to others. So your degree of multiprogramming is low there. Next, so if you are here, there are too few number of frames. This is for each process, right? So this is for a process, some p sub I. Ith process. So minimum to get started, minimum number of frames to get started. But if you are at a low number, just above that minimum, then you have too few. So when you have too few, what are you saying? I needed 2 frames to get started. I got the 2 frames, but my page number requests, page references are, say, from a set of 4, right? So I've got allocated 2, so I can get started, but my page references have, say, 4 options, 1, 2, 3, 4. At any given time, I will have 2 frames in the physical memory, but I need 2 more, right? So for that 2 more, I'll have a lot of page faults. So too few frames allocated, so that particular process is going to be thrashing, right? I needed 4 to make sure that that thrashing doesn't happen, but I got only the minimum. Let's see. If you go all the way over here, then you have too many, which is good news for that particular process, but it is wasteful in general because you could have used those extra frames to run more processes. You could have been over here somewhere and have a high degree of multiprogramming. If you are here, the degree of multiprogramming is low, very low, as we discussed earlier. Questions here? This is about, how many frames do you allocate, close to the minimum or close to the maximum. You, of course, cannot go here because you have a limitation on the physical memory. You can go here, but there is no other choice but to suspend that process, right? Straightforward? Yeah, all right, let's go on. Talk about thrashing. So if a process does not have enough pages, its page fault rate is going to be very high. I do not have enough frames to make progress. I continuously have, just make up a simple scenario. Suppose you have only, say, 2 frames, right? This is, say, frame 0, then this is frame 1, right? And your page references, page reference string is, say, 0, 1, 2, 3, 1, 2, 3, and so on, right? This is my page reference string. So this particular process is trying to request page 0, page 1, page 2, and 3. These are all page numbers. Well, if it goes this way, how are you going to fit in? Page 0 is not there, so you will first bring it in over here. Next, you will ask for page 1. It's not there, so you will bring it on over here. And what are you doing after that? 2, 3, 1, 2. Continuously, you're doing page faults, right? So you're replacing page replacement because you had 4 options and you had only 2 frames. So its page fault rate is now going to be very high because of that, right? A process is thrashing if it is spending more time swapping pages in and out than actually making progress. So if you're just doing page faults, then you're not making progress on that process. That's thrashing. And a system is considered to be thrashing if several of its processes are thrashing. The entire system is then thrashing, not making any progress. Questions here? Let's move on and talk about a simple solution. The simple solution is observe, monitor, watch the CPU utilization. How much is your workhorse working for you? if the CPU utilization is low, increase the number of processes. So if it is too low, then you launch more processes. When you launch more processes, then you're saying, CPU, if you cannot work on process 0 or process 1, I will give you 3 more options to work on so that you are busy, right? But of course, the problem is that if you increase that number to too many, then they have to split the physical space. We will have thrashing again. So, but this can be a simple solution to get started, right? Like at the initial stage. So watch the CPU utilization. If it is too low, launch more processes. But this is going to lead to a vicious cycle, which is explained over here. Let's talk about this first at the top. Operating system monitors the CPU utilization. If the CPU utilization is too low, then it launches more processes. So instead of 2 processes now, we have 10 now, right? Launch more processes. So as you launch more processes, the CPU can now start working on it, which is good, but we also have to allocate frames to it, right? So new processes will get allocated frames from other processes. Earlier, those processes, those frames were allocated to 2 processes. Now they are allocated to 10, which means that each process is now going to have fewer. So other processes will start page faulting because now their numbers went down. So if other processes page faulting, that means that the CPU utilization decreases, right? If the CPU utilization decreases, then you launch more processes. So what is going to happen here? This is going to, like, if you just follow that simple strategy and not stop it somewhere, like we have got to adapt to this problem. We have to find a way to break this vicious cycle. And we'll talk about certain ideas there. But I hope you see that if you don't, this is going to continue, right? CPU utilization is low, launch more processes. As you launch more processes, each process will start thrashing. Each process will start thrashing. That means CPU utilization is going to go down because now it's not working. It is just, swapping pages in and out. You are back over here, which means you launch more processes. So now you're just going to launch more processes indefinitely, right? So we are going to need to find a way to allocate frames that breaks that cycle, some strategy, some policy that breaks that cycle. So let's take a look at a graph here. And this graph on the x-axis, it has degree of multiprogramming, which essentially means how many processes are you working on? That's x-axis. And the y-axis is CPU utilization. So what do you want? You want to be here, right? You want your degree multiprogramming to be high. I can work on 10 processes at once. So you want your degree of multiprogramming to be high, and you also want your CPU utilization to be high. So this one is going to be your sort of good zone here. What happens here? Degree of multiprogramming is low, CPU utilization is low. Why is that? Well, you have 1 process, 2 process, 3 process, right? Very few number of processes that you have. And CPU utilization is very low over there. Why is that? When you have low, if you page fault, you don't have anything else to work on, right? So if you don't have anything else to work on, you just stall. You do nothing. So CPU utilization is low. Now, as you increase the degree of multiprogramming, your CPU utilization is going to go up because now the CPU is going to definitely have an option to work on, even if a process page faults. You can do that up to this particular point. After that, you would have allocated too many frames, you would have launched too many processes, right? Degree of multiprogramming is too high. Number of frames for each process become too low. If number of frames for each process become too low, you will get into this thrashing scenario where all the processes are like page fault, page fault, page fault. I don't have enough frames. So then the CPU utilization dramatically goes down after that. There's a steep slope there because everybody is thrashing and the system goes in the thrashing mode. And that is going to be your bad performance, right? Like you don't want to be there. So you want to be here. This is better than this. Because over here, if you are here, maybe the available number of the number of processes are low, right? So you may not have the need to work on more processes. That's fine. And the CPU utilization is okay. It's on the uptick. So even if you launch more processes, you would have increased CPU utilization. You can still take that. This is your best case scenario, right? Best of both worlds. Degree of multiprogramming is good, CPU utilization is good, but you definitely don't want to be here. Questions here? Good. So you would want to be over here somewhere, right? You don't want to go too close. So so here, a better way to answer that would be, the user is launching processes, right? So as the user is launching processes, the operating system in the background is responding to those active processes by allocating frames to it. So it's the user who has to sort of, and there is no good way to do it, right? Like the user can stop over here, say stop over here, but the user is not going to know, right? The user is not going to know, oh yeah, what is my degree of multiprogramming versus CPU utilization? They are just going to start, oh yeah, I started Chrome and then I started Firefox and I started this. They are just going to launch processes. So the operating system is going to have to monitor either the page fault rate or the CPU utilization, and in response, it can do a few things. One, it can suspend a process, right? Okay, you have launched too many, I'm going to suspend a process. And then you can have scenarios, right? On what basis are you going to pick the process that gets suspended? Hopefully a low priority one, or something very small or something large, depending on how things are going at that point. So suspending processes is what happens in a realistic scenario there. So I'm going to have to cut back. So you bring it back. And the operating system for that suspension, it can monitor two things. One, CPU utilization, or an alternative technique is to monitor page fault frequency. And we'll talk about that second approach in a little bit. All right, so too few problem thrashing for the few processes. Too many frames that are allocated for each process, that is also very bad because the degree of multiprogramming is too low over there. So we are going to have to find just right number of frames. So how are you going to do that? That sweet spot. How are we going to know? Well, we are going to have to understand the process, right? We are going to have to understand the needs of the process, each process, and fix that number for that. It's not going to be the same for everybody. It's not going to be the same for every process. So we can take a look at locality of each process and then assign number of frames, the allocation for each process based on the locality. So when we talk about the principle of locality, what did we say? There are two types, right? Temporal and spatial. So temporal says what? The x-axis over here is execution time. The y-axis over here is memory addresses. And each dot over here corresponds to a memory access. So if you are bunching on along the x-axis over here, that means that execution time is very correlated, right? So what that means is you are getting a memory access for the same memory address or nearby memory addresses as the time goes on, right? So in a given time window, you're accessing some things that are nearby in memory address space. The probability for that happening is very high, right? So when the memory accesses are bunched up along the x-axis, that is called temporal locality, right? That's execution time. So that's over here, temporal locality, bunching along the x-axis. So what we can do is we can monitor this, and we can say, all right, in this amount of time, if I allocated the frames that correspond to those many memory addresses, I would have been fine. All of those would be in my physical memory, and I wouldn't page fault, right? So I can base it on locality. Now, one problem. You see over here, that is the size of my temporal locality. What about here? Bigger than that, right? So if I started off with this number and I allocated that many frames, well, I could have a scenario where my temporal locality for that process changes over time. What do you do then? which means we could still have thrashing, right? So thrashing could still occur, even if we follow principle of locality and assign frames based on that. We could still have the problem of thrashing because this could still happen. Total size of locality could be greater than the allocated memory size. We could have a oval here which is longer than the what we have allocated to it. And the same applies for even the spatial locality, right? Spatial locality is in terms of memory addresses, right? So bunching along the y-axis. You will tend to access nearby memory addresses often, like a for loop. This, repeatedly. So if you have that, that also could be longer. So both in terms of time and in terms of space, your locality can change over time. So far, the policies that we have talked about, those are static. Size, priority. We have not talked about changing that, right? So we are going to talk about a model, a working set model, where we take a look at the locality, but we also change it from time to time, right? So the operating system manager will sort of adaptively change the number of frames allocated to each process, which is but each computation is based on locality. We'll take a look at an example there. So working set model. Working set model is the set of frames that a process is actively working referencing is called a working set. Like I said, you see, if I go back to this particular example, right here, page reference string 0, 1, 2, 3, 1, 2, 3, right? So if I look at all of these page requests, my working set is what? 0, 1, 2, 3. Right? So if I just look at the page reference string here, which is 0, 1, 2, 3, 1, 2, 3, it belongs to a working set of 0, 1, 2, and 3. Those are the unique page requests that have come in. No other page requests have come in. So if I look at a time window here, from here to here, hopefully, and hopefully that is corresponding to the locality of that particular process, then I only have to have 4 frames, right? And I would have taken care of that. No page faults in that case, if I had 4 frames there allocated to this process. So a working set, let me go back to that definition. Working set essentially means how many page requests that are unique that are coming in. There you go. Set of frames that a process is actively referencing. It was referencing only 4 different ones. So that those 4 different ones belong to a working set, and we'll call this simply WS, working set. Our strategy can be allocate each frames to satisfy the current working set. So in my example earlier, my current working set was 0, 1, 2, and 3. I will allocate 4 frames to it. It will take care of all those page references, right? I had how many? 7 page references? 0, 1, 2, 3, 1, 2, 3. So 7 page references. And I could have taken care of those 7 page references with only 4 frames allocated to it. So that's what it says. Allocate enough frames so that we satisfy the current working set. And I hope you see that our working set could have been bigger or could have been smaller, but in either case, we are leveraging locality, right? Because the chances of you to have repeatedly, at least in terms of the numbers, being close by are very high. Repetition is also very high, right? So something like 1, 1, 1, 2, 3, 1, 1, 1, like that, the chances of that happening are very high as well. Now, if there are enough extra frames, you have done that allocation, right? So you have looked at the working set and you have allocated the frames. Now, if you have enough extra free frames, after that allocation, if you have free frames, increase the degree of multiprogramming. I have got this one process covered. I still have a lot of extra free frames available. I will launch more processes to increase CPU utilization, increase degree of multiprogramming, launch more processes. But this could lead to a problem. Everybody is fighting for the same amount of physical space. So if the sum of working set sizes for all the active processes exceed the total number of frames that are available, you decrease the decrease the degree of multiprogramming. So instead of going to 100 processes, stop at 90, right? You guys see how this is going to work? Here we are keeping track of degree of multiprogramming. How many number of active processes do you currently have working, while satisfying the working set size of each one, right? So you look at the working set size of process 1, 4 frames done there. Okay, I have 96 available to me. How do I allocate 96? Well, I need something to allocate this to, increase degree of multiprogramming. Okay, now I've got a few processes to choose from. All right, let's allocate 8 to this guy, 10 to this guy, and so on. Once you allocate all of them, if the allocations that you have made are more than the number of frames that are available, then you are in a problem. So now you start decreasing the degree of multiprogramming. You see how this is going to work? All right. Let us do some math with this, and we'll also take a look at an example. So delta is our working set window. So this is a time window over which we are looking at the page references, right? So the example that we took, 0, 1, 2, 3, 1, 2, 3, those were the time window was 7, right? So delta was 7 for that. It is a fixed number of page references. Yeah. Next, WSS sub I, working set size for a process I. The size of the working set process, it is essentially total number of unique, I should highlight this, unique page references in the most recent delta. So let me go back to my example here and talk about what delta is and what WSS is. I'm giving you only this, and I'm taking a look at that, right? So I'm taking a look at starting 0, ending at 3. So that is going to be my time window over which I'm looking at all the page references. So in this case, delta is how many? 7, right? Fixed number of page references that I looked at, 7. What is my working set size here? 4. Unique pages, 0, 1, 2, 3. That's it, 4, right? So delta is the time window or working set window. Working set size is your unique pages in the recent time window, in the most recent delta references in the past. Now, delta is a parameter of this working set model that could be too small, could be too large, or could be infinity, right? So what happens if delta is too small? Well, if delta is too small, you are looking at only the last 2 or the last 3, like only a few. Your time window is very, very small. So if your time window is very small, and if you base your, what is the working set size going to be? If delta is small, can I say that the working set size is also going to be very, very small? In general, so you're going to allocate very, very few frames to it, right? If you assign very few frames to it, then you're not going to encompass the total locality. Instead of allocating this, if your time window is short, then you're probably only allocating that. You're not allocating the entire thing. So if delta is too small, then you will not encompass the entire locality. In other words, you may have a high page fault rate, because if you are not leveraging locality, then this is not going to work really well. You will still be doing page faults. Now, if delta is too large, then you are encompassing the total program, right? So if it's too big, then you are taking care of this locality here, all of it. So the entire program is there, which means what? Degree multiprogramming is going to be low. You have nothing left for others to work on if you based your frames on delta. Delta is infinity. That is, entire program is there, right? You're looking at the entire program. So delta is the time window over which you are observing a fixed number of memory references. If it is too small, then you are not encompassing the total locality, just a portion of it. If it is too big, then you have so you're going over the locality. If it's infinity, that's total and total program. Cap D is the total demand frames, which is essentially take each process and add up all their working set sizes. So all the unique page numbers, all the unique page references for each process, just add them up. In our example, we had 4 unique pages, right? Like that, for each process, compute the working set size and add them up. When you add them up, you are going to know how many total demand frames. That's our total demand frames. Now, if total demanded frames are greater than the total number of frames available, then we are thrashing. And how do we respond? We suspend one process. We pick a process that is of low priority, and then we try to suspend that and see if D is equal or slightly less than the number of frames that are available. Right? We cannot demand more than what is available. If we do that, obviously we'll be thrashing. Let's take a look at it, this working set model with an example. Hopefully over here it will become pretty clear. How are we estimating our number of frames to allocate for each process? So here we have, what is this? This is an example of page references. It's called a page reference string for a process. So the CPU is generating a virtual address that corresponds to the physical address with the frame number, or with the page, the virtual address with the page number 4, 2, 6, 1, and so on as time goes on. Right? So those are page references. So as your as the CPU is requesting these specific pages for a process, for this process, and let us say our delta time window is 10. So we are looking at 10 is what? The fixed number of page references. Say we make this observation at T1 and at some other time T1 plus small t, right? We are making this estimation of working set and working set size at 2 different times. One at T1, one at T1 plus t. So if you look at the last 10 page references at the time T1, what do you have? The working set is going to be 1, 2, 6, 5, and 7. That's my working set. My working set is the unique page requests that have come in. The number of them, well, 1, 2, 3, 4, 5. 5. I was referencing 5 unique pages in the last 10 page references, which means if I had allocated 5 frames to this particular process, I would have been good, right? Good here, really, really good here, right? So let's take a look at this estimation at some other time T1 plus T. So if you are looking at T1 plus T, last 10 page references are highlighted in blue. The working set over here is just 3 and 4, right? Those are the unique page requests that have come in the last 10 page references. And the size of this is just 2 pages, so 2 unique pages. So when the operating system manager tries to allocate frames, it can use this working set size estimation to do that allocation. It can keep it at 5. It is going to be good. But at a later stage, if the locality increases, if the locality is going to increase, I may have a working set size of more than 5. Maybe I go to 7. In that case, I can adapt the number of frames for that process, provided I have some frames available for it. Or else, I will just keep it at 5. You can see that? Now, we talked about delta, right? So let's see. You can have a small delta, you can have a very big delta. If delta is too small, then over here, you're looking at only, say, these 2, right? Or these 3. You're only looking at a very few most recent page references. And if you do that, we have a problem. We are not encompassing the locality, the entire locality. Delta is too big, right? From here to here, for example, then we are going over the locality. So we would want that delta to be chosen in such a way that it is very closely related to something that is close to those numbers, right? The localities of those programs. Okay, let's go back here. How about T1? Sorry, T1 could be anywhere. How about T? So that is one parameter here, delta. We could have changed that. How about T? What happens when you make T very small or very big? When you make this working set size estimation, suppose T, small t, is very small. If you're too small, then you're overlapping on the basis of temporal locality, right? The localities are overlapping. It's not a very useful way to estimate the number of frames. On the other side, if you make t very big, then there's no locality here. There's no correlation over here, right? So you cannot be too small, then you're overlapping localities. If you're too big, then you don't have any correlation between this locality over here and that locality over there. So the times at which you are computing those number of frames should also be reasonably close, not too close, right? So again, a balance for delta, a balance for small t. So with suitable choice of delta and t, we can get a reasonable estimate of the true set size. Using this estimate of true set size, we can allocate the number of frames to match that true set size. Usually this is done experimentally and then it is later tuned by the system manager. So experimental for that particular process, find out these numbers, then you tune it at the end by the system manager. Questions about this working set size estimation? We are just trying to come up with a number. What is that? Frames allocated for a particular program. And with the working set size or working set model, we are looking at the principle of locality to come up with that particular number. Okay. All right. A slightly different approach to assigning the number of frames. This is based on monitoring the page fault frequency for a process. So let us try to observe how often are we getting page faults for a process. How do you find out page fault rate? You divide the number of page faults by the total number of page references, right? So that's how your page fault rate. If that page fault rate is too high, right here, suppose you are over there, page fault rate is too high. What do? Well, you can increase the number of frames for that particular process, right? So if you have only 2 frames for a process, you are page faulting a lot. You increase the number of frames, you make it 4, then you are maybe not page faulting as much, right? So if you are over here and you keep track of page fault rate, if it is too high, you increase the number of frames for that process. And when you do that, you will bring this page fault rate down. Okay. Next, if you keep increasing the number of frames, it'll keep going down, keep going down, keep going down. But it will cross this lower bound where you will have a very, very low page fault rate for a process. However, there is not enough frames for other processes, so the degree of multiprogramming goes low over there. So that's your second problem. So in order to solve the second problem, what do? You decrease the number of frames for that process. You bring it back up, right? So what you want to do is work between a upper bound and a lower bound that is indicated by a system manager. So continuously look at the page fault rate, be between those 2 bounds. And if you are over here, you increase the number of frames. If you are over here, decrease the number of frames for that process so that you bring it down to this particular sweet spot between the 2 bounds. Because if you are between the 2 bounds, your page fault rate is low enough while keeping the degree of multiprogramming high enough. Questions? Go ahead. Yeah. So you're talking about this particular one, right? So this is lower bound. So you want to, well, this particular lower bound is sort of an arbitrary number that is, you, each user can define that. The person who is writing that application can define that. Okay, I need these many to make sure that this works. Beyond this, you can, so the lower bound is sort of a application, the person who wrote the application, he or she sets that. So I need enough, right? So if you, so basically, if I have too many beyond this, I may not need this. Like you can use these extra frames. Don't increase anymore because you can use it for other applications. Let's see, okay. So just to summarize our page fault rate, paging, essentially pages in the virtual memory, the issues that we talked about that. When should we bring a page into memory? From where? From the hard disk to physical memory, right? That's where we are bringing the page to physical memory. And then we are accessing using the virtual address mapped to physical address. When should we do that? Valid bit is 0 and so on, right? Which page gets replaced and in what basis? We talked about the three, well, we've talked about a few more replacement algorithms. FICO, the optimal, least recently used, and also second chance FIFO and approximate LRU. Those were the algorithms that we talked about for page replacement. And then today we talked about how many frames do you allocate for a process. What are you going to base it on? Equal allocation, size proportional allocation, proportional to the priority of the process, working set model, and the last one was to monitor the page fault rate for a process. So that completes our discussion on pages. You guys can work on the activity for today. Let's see, exam on Thursday. Similar logistics, whoever wants to come in can come in, whoever wants to be online can be online. You will be proctored here and there. What else? What else do I need to? Oh, what are the topics for exam? It's going to essentially be control unit, right? Control unit, which was, I believe, lecture 9 or 10, somewhere there. Pipelining, and then memory. So the lecture today is not going to be on the exam, but so until page replacement algorithms, until what we did last week, you can expect on the exam. Generally, this one is simpler than the first exam, so you guys should be okay. That is all I have for you guys. I know that this is a busy exam time for most of you, if not all of you. So I wish you the best for your exams. I'll stop recording here.